Welcome to The Explainer. I'm your host, Dr. Chem. Today we're exploring something that is honestly visually stunning, paper chromatography. Just imagine breathtaking macro shots of colorful inks spreading across paper fibers under dramatic lab lighting. It is a remarkably simple technique, yet it transforms complex chemical mixtures into these quantifiable, brilliant bands of color. It's a fundamental scientific process that has quietly shaped our modern world, and today we're decoding exactly how it all works.
Okay, let's dive into this. Picture yourself as a forensic investigator, right? A crime lab receives a ransom note. How do you trace that specific piece of paper back to a single suspect's pen? To the naked eye, the black ink looks perfectly uniform. But beneath that solid color, there's a whole complex mixture just waiting to be unlocked.
The Ink Detective's Toolkit.
So to solve our forensic mystery, we actually don't need a million-dollar machine. We just need a really elegant, clean laboratory setup. We start with a specialized piece of porous chromatography paper. Near the bottom, there's a horizontal line, which we call the origin. We carefully apply our extracted ink spot right on that baseline. And here's an absolutely crucial detail. That line must be drawn in pencil. Why? Well, because the graphite lead is completely insoluble in our experiment. It simply won't move. If we were to draw it with a pen, the line itself would separate and completely ruin our data.
Now, the real magic of this technique is that inks are usually mixtures of several different chemical compounds. We can literally force them to separate out based on their unique chemical properties, specifically their polarities. Because each compound has a slightly different molecular structure, they travel at different speeds. If you could see the intermolecular interactions happening, it would look like glowing molecules separating into distinct, brilliant bands of color right before your eyes.
Section 2. Physics of the upward flow. So how exactly does the liquid move up the paper to push these colors apart, especially without any pumps or motors? Well, it all comes down to a natural phenomenon known as capillary action. To make this super intuitive, just think of a sponge or a paper towel soaking up a water spill on your kitchen counter, or even how tear fluid continuously drains in your eyes. The liquid is actually able to flow in microscopic narrow spaces, completely defying external forces like gravity.
And the mechanics here brilliantly illustrate exactly how that flow happens. It's totally driven by intermolecular forces. Adhesion is the force that pulls the liquid to the solid inner walls of the cellulose paper fibers. Meanwhile, cohesion, which creates surface tension, keeps the liquid molecules bonded together, basically dragging the whole column of fluid upward. And the narrower those microscopic gaps in the paper are, the further the liquid gets pulled. This is actually the exact same mechanism that allows towering trees to pull water from their roots all the way up to their highest leaves.
And here's a fun, surprising historical fact for you. The very first recorded observation of capillary action was actually made by the great Leonardo da Vinci. It has fascinated brilliant minds for literally centuries. In fact, Albert Einstein's very first published scientific paper, way back in the year 1900, was completely dedicated to the physics of capillarity.
Section 3. Stationary and mobile phases.
To truly grasp chromatography, you've got to understand that every setup requires this sort of chemical tug-of-war between two very distinct phases. First up, we have the stationary phase. In our case, this is the porous filter paper itself, which contains cellulose and a very thin layer of adsorbed moisture. Second, we have the mobile phase. This is the traveling liquid solvent, something like water, methanol, or isopropyl alcohol that physically moves up the paper. The components of our ink mixture are partitioned based on their affinity. They're basically constantly deciding, do they want to stay anchored to the stationary water in the paper, or do they want to dissolve and ride the wave of the moving solvent?
Let's walk through the actual laboratory procedure. Returning to our forensic investigator, they first extract the ink from that ransom note with a bit of methanol and carefully apply it as a spot on our baseline origin, usually using a tiny capillary tube. Next, they place the paper into a glass developing chamber, being extremely careful that the liquid solvent level sits perfectly below that origin line. Finally, we just watch. Through capillary action, the mobile phase moves up the paper, creating these mesmerizing, time-lapse-like sequences as colorful compounds separate into distinct bands.
Section 4. Calculating the RF value. Let's move to and see how this builds from a beautiful visual into hard, quantifiable data. Now, what's really interesting about this calculation is how we measure two specific distances to get our results. Distance B is the total distance traveled by the solvent front from the origin. Distance A is the distance traveled by our specific separated ink spot. And here's a critical instruction for you. Distance A must always be measured from the origin to the exact middle of the separated spot. That ensures our accuracy.
These measurements give us the retardation factor, or RF value. It's a really simple math formula. RF equals distance A divided by distance B. Because each specific dye has its own unique chemical structure, it's always going to yield a unique RF signature in a given solvent. So by comparing the RF values of the ink from the ransom note to the ink from our suspect's pen, we can definitively solve our mystery.
It is important to note, though, that 1.00 is the absolute maximum possible RF value you can achieve. That number only happens if a solute compound has absolutely zero affinity for the stationary paper phase and travels perfectly, 100% in sync with the mobile solvent front.
Section 5. TLC versus Paper Chromatography. Let's briefly zoom out and compare our traditional paper technique with its slightly more high-tech sibling. Paper chromatography is incredibly accessible. It uses standard filter paper, it's very cheap, and it's absolutely excellent for quick, preliminary chemical separations. However, thin-layer chromatography, or TLC, steps it up a notch. Instead of paper, TLC uses an adsorbent like silica gel coated onto a solid plate. This allows for much sharper separations. TLC plates can also withstand higher heat, corrosive reagents, and they offer a significantly higher sensitivity for detecting tiny trace amounts of a substance. But both remain incredible tools in the modern lab.
Section 6. Real-world scientific breakthroughs.
I want to transition now to the profound historical impact of this simple paper technique, because it is definitely not just for testing markers. So the crucial point is that this exact method unlocked some of the greatest secrets of life itself. Think about this. Frederick Sanger used paper chromatography to figure out the exact structure of the insulin molecule. Melvin Calvin used it to map out the complex reactions of photosynthesis in green plants. Erwin Chargaff modified the technique to reveal the base pairs of nucleic acids, and it was that exact data that James Watson and Francis Crick used to deduce the double helix structure of DNA. How incredible is that?
And this technique remains highly relevant today across so many scientific disciplines. Forensic scientists use it to analyze explosive residues from blast sites and investigate forged documents. Food scientists rely on it to detect illegal synthetic colorants in our drinks and sweets, basically keeping us safe. Pharmaceutical laboratories use it constantly for quality control, monitoring active ingredients and isolating impurities in life-saving medicines.
From breathtaking macro separations of vibrant pigments spreading across paper fibers, all the way to identifying the very building blocks of DNA, the principles of chromatography show us just how elegant science can be. It's a brilliant reminder that sometimes the most powerful analytical tools are also the simplest. So, what complex mysteries will a simple piece of paper unlock next? I'm Dr. Chem. Thanks so much for joining me for this explainer. I'll see you next time.